The universe is vast, mysterious, and filled with questions that continue to defy human understanding. For centuries, we've explored the cosmos with ever-advancing technology, from ancient stargazers to space telescopes that peer billions of light years away. Yet every discovery reveals even deeper enigmas. What came before the Big Bang? Why does the universe expand faster than expected? And what unseen forces shape the fabric of reality itself? Despite all our progress, space still hides more than it reveals, reminding us that the greatest mysteries lie far beyond our reach. In this journey, we'll uncover 100 of the most baffling cosmic secrets that science still can't explain, each one a glimpse into the infinite unknown that continues to challenge everything we think we know about existence. So, watch this video till the end and subscribe to the channel. Let's begin. From the moment we first looked to the stars, one question has loomed larger than all others. How did everything begin? The Big Bang Theory tells us that the universe began about 13.8 billion years ago, from an unimaginably dense point, expanding outward to create all space, time, and matter. Yet even this monumental idea leaves us with a haunting mystery. What caused it? Science can trace the cosmos back to a fraction of a second after its birth. But before that, our understanding collapses. At that moment, known as the singularity, the laws of physics simply stop working. Some theories suggest that our universe emerged from quantum fluctuations in a vast cosmic vacuum, where energy briefly surged into existence and inflated into the space we now inhabit. Others imagine that we live in a cycle, a universe that expands, collapses, and is reborn again and again in an eternal rhythm known as the Big Bounce. But what existed before the beginning, before time itself, remains one of the most profound enigmas in all of science. Even more puzzling is that the universe isn't just expanding, it's accelerating. When astronomers first discovered this in 1998, it defied every expectation. Gravity should be slowing cosmic expansion, yet galaxies are flying apart faster and faster. To explain this, scientists proposed something extraordinary: dark energy, an invisible force that makes up roughly 68% of the universe, yet remains completely undetectable except through its effects. It acts like a cosmic repulsion, stretching the fabric of space itself. Some physicists think dark energy might be an inherent property of the vacuum, the energy of nothing, while others believe it could be a dynamic field that changes over time. Whatever it is, it controls the fate of everything, deciding whether the universe will expand forever, tear itself apart, or collapse back into darkness. But even the existence of matter, the stuff that makes up stars, planets, and us, is a mystery. According to the laws of physics, matter and antimatter should have been created in equal amounts during the Big Bang. When they meet, they annihilate each other completely, leaving behind pure energy. Yet somehow, a tiny imbalance occurred. For every billion particles of antimatter, there were 1,000,001,000 particles of matter. That single extra fragment in every billion is why anything exists at all. Scientists still don't know why this asymmetry happened. It could be that certain subatomic particles behave slightly differently than their mirror opposites. But even our most powerful particle accelerators have yet to reveal the full reason for this cosmic favoritism. And then there's the question that haunts modern cosmology. Why does the universe exist rather than nothing? Physicists can describe how things unfolded after the Big Bang, but not why there was something to unfold in the first place. Some theorists suggest that nothingness is unstable, that quantum laws make the spontaneous creation of universes inevitable. Others propose that countless universes exist in a vast multiverse, each with its own physical laws, and we simply live in one where conditions happened to allow life. Yet, every time we peel back a layer of the cosmos, it seems to whisper the same message. creation itself is still beyond our reach to fully comprehend. And so, from the mystery of the first spark to the invisible hand of dark energy driving the universe apart, our search for cosmic origins reminds us that every answer is only the beginning of a deeper question. The story of the universe's birth is still being written, and we're only beginning to understand the first line. As we journey deeper into the cosmic unknown, we find that most of the universe isn't made of stars, planets, or even the visible matter we can see. It's made of something utterly invisible, something we can't touch, detect, or even fully describe. Astronomers call it dark matter, and although it doesn't emit or absorb light, its presence is undeniable. The first hints appeared in the 1930s when Fritz Zwicky studied the Coma cluster and noticed that galaxies were moving far too fast to be held together by visible matter alone. Later, in the 1970s, Vera Rubin confirmed this mystery on a galactic scale. Stars at the edges of spiral galaxies were orbiting just as quickly as those near the center, when, by all logic, they should have been flung into space. The only explanation was that an unseen mass, a vast halo of invisible substance, was exerting a powerful gravitational pull, holding everything together. But despite decades of searching, we still have no idea what dark matter actually is. Every experiment designed to catch it, from underground detectors buried deep in mines to sensitive instruments aboard satellites, has come up empty-handed. It's as though dark matter refuses to reveal itself. We can see its gravitational fingerprint shaping galaxies, bending light through gravitational lensing, and sculpting the large-scale structure of the cosmos, yet not a single dark matter particle has ever been directly detected. Scientists have proposed countless candidates to explain this invisible mass. One leading idea is that dark matter is made of WIMPs, weakly interacting massive particles, that barely interact with normal matter except through gravity. Others suggest axions, hypothetical ultralight particles that could fill the universe like an invisible ocean. Some physicists even look to more exotic possibilities, like sterile neutrinos, or suggest that dark matter might not be particles at all, but primordial black holes, tiny remnants from the universe's earliest moments. Each possibility fits some observations, but fails in others, leaving the true nature of dark matter shrouded in uncertainty. What makes dark matter even more elusive is its complete indifference to light. Unlike ordinary matter, it doesn't emit, reflect, or absorb electromagnetic radiation, which is why telescopes can't see it directly. It passes through stars, planets, and even us without leaving a trace, detectable only by the gravitational effects it exerts. This invisibility makes it both fascinating and maddening for scientists. A cosmic ghost that shapes the universe yet remains unseen. Still, not everyone agrees that dark matter is the only explanation. Some physicists propose alternative gravity theories like MOND, modified Newtonian dynamics, and TeV-S, which tweak the laws of gravity themselves. Instead of invoking an invisible substance, these theories suggest that gravity behaves differently at cosmic scales, stronger in the outer regions of galaxies than Einstein's equations predict. While such ideas can mimic dark matter's effects in some cases, they struggle to explain large-scale observations, such as the cosmic microwave background and galaxy cluster behavior, as neatly as dark matter does. The truth may be far stranger than anything we've imagined. Perhaps dark matter is not one thing, but a collection of phenomena, or maybe our understanding of gravity itself is incomplete. Whatever the answer, dark matter holds one of the keys to the universe's structure, evolution, and fate. Until we find it, we're living in a cosmos where the invisible outweighs the visible, and the universe hides most of its mass behind a veil science has yet to lift. As we move from the invisible realm of dark matter to the dazzling architecture it helps shape, we find ourselves staring into one of the universe's grandest spectacles: galaxies. These cosmic cities of stars, dust, and dark matter stretch across unimaginable distances, swirling and colliding in a slow cosmic dance. Yet even these colossal structures, home to hundreds of billions of suns, are riddled with mysteries that continue to challenge our understanding of cosmic evolution. At the heart of nearly every large galaxy lies a supermassive black hole, millions or even billions of times the mass of our Sun. Our own Milky Way harbors one, Sagittarius A, a monstrous object lurking quietly 26,000 light-years away. But the mystery isn't just their presence, it's how they formed so quickly. Observations have revealed black holes that existed less than 1 billion years after the Big Bang, already reaching staggering sizes. According to our models, black holes should grow over time by consuming gas and merging with others. But these ancient giants appeared too soon. How could something so massive form in a universe still in its infancy? Some theories suggest they were born from the direct collapse of gigantic primordial gas clouds rather than the remnants of dying stars. Others hint at exotic physics, like dark matter's gravitational role in feeding early black holes. But for now, the rapid rise of these cosmic titans remains one of astronomy's most puzzling riddles. Adding to the enigma, astronomers have discovered something that seems impossible: galaxies without dark matter. In 2018, researchers identified several faint galaxies that moved in ways suggesting they contained little to no invisible mass at all. Since dark matter is believed to be the glue holding galaxies together, their existence defies logic. How can such galaxies stay intact if they lack the very framework thought to bind them? Some suspect they may have formed from tidal debris during galactic collisions, temporarily shedding their dark matter halos. Others think these could be observational illusions, where unseen factors mask dark matter's influence. But if they truly exist, they force us to reconsider everything we believe about how galaxies are built. Then there's the enduring beauty of spiral galaxies, their arms sweeping gracefully outward like cosmic pinwheels. According to basic physics, such structures should blur over time. The stars in the outer arms orbit slower than those near the core, which should cause the spiral pattern to wind up and vanish. Yet galaxies like the Milky Way have maintained their elegant forms for billions of years. The secret may lie in waves of density rippling through the galactic disk, gravitational traffic jams that cause stars and gas to cluster along specific paths, continually renewing the spiral structure. Still, the exact mechanism remains unclear, as every simulation brings more questions than answers. When galaxies do collide, the results are both violent and spectacular. Despite their vast populations, the stars within them almost never crash directly. The distances between stars are so enormous that they pass harmlessly by each other. Instead, gravity stretches and distorts the galaxies themselves, triggering bursts of star formation as clouds of gas are compressed and heated. Over millions of years, the two galaxies eventually merge into a single, larger system. Our Milky Way, for instance, is on a slow-motion collision course with the Andromeda Galaxy, a cosmic event that will unfold about 4 billion years from now. The stars will dance through one another, and their supermassive black holes will eventually merge in a cataclysmic release of energy, reshaping both galaxies forever. But perhaps the most profound mystery lies not within individual galaxies, but in the cosmic web that connects them. Across the vast expanse of the universe, galaxies are not scattered randomly. They align in colossal filaments, forming intricate structures that span billions of light years. Between them lie enormous voids, vast regions almost completely empty. This filamentary pattern resembles the neural structure of a brain, hinting at a hidden order behind the chaos. Astronomers believe that dark matter played a major role in sculpting these webs, pulling ordinary matter into threads that later birthed galaxies. Yet, we still don't know why the universe formed this way, why structure emerged in such striking patterns rather than in simple clusters. It's as though the cosmos follows a blueprint we've only begun to glimpse, one written in the invisible forces that govern all creation. And as we trace these grand galactic shapes through time and space, we realize that every spiral, every collision, and every filament is part of a deeper mystery, one that links gravity, matter, and the unseen in a single, beautiful equation we have yet to solve. From the swirling hearts of galaxies to the darkest regions of space, we arrive at perhaps the most terrifying and fascinating objects in the cosmos: black holes. These are regions where gravity has triumphed completely, where the pull becomes so immense that not even light can escape. They are the final stage of massive stars and the ultimate mystery of physics, warping both time and space in ways that defy human comprehension. Yet, despite decades of study, what truly happens inside a black hole and what these cosmic abysses might mean for the universe remains one of the greatest puzzles in science. A black hole's defining boundary is known as the event horizon, the point of no return. Once anything crosses it, all paths lead inward, crushed inevitably toward the center. But what lies beyond that horizon is a mystery that even Einstein's equations cannot fully describe. General relativity predicts that at the core sits a singularity, a point of infinite density and zero volume where space and time break down entirely. In this realm, gravity becomes infinite and all known laws of physics cease to apply. Yet quantum theory insists that infinities cannot truly exist. Something must prevent the collapse from reaching absolute nothingness. Could there be another form of matter or a hidden structure that replaces the singularity? Or perhaps a bridge to another region of space-time entirely? For now, the inside of a black hole remains hidden behind a veil that no observation can pierce. This leads us to one of the most profound conflicts in modern physics: the black hole information paradox. According to quantum mechanics, information about matter, its physical state, properties, and quantum details can never be destroyed. Yet, when something falls into a black hole, it seems that information is lost forever, swallowed by the void. Stephen Hawking's calculations in the 1970s suggested that black holes aren't completely black. They emit a faint glow known as Hawking radiation, caused by quantum effects near the event horizon. Over immense timescales, this radiation could cause a black hole to slowly lose mass and eventually evaporate entirely. But if that happens, where does the information go? Does it vanish, violating quantum theory, or is it somehow encoded in the radiation itself? Recent theories propose that information might be preserved on the event horizon in a kind of cosmic hologram, a two-dimensional imprint of everything that falls in. Still, no one knows for sure, and solving this paradox may be the key to uniting quantum mechanics and general relativity once and for all. The mystery of how black holes grew so quickly after the Big Bang also remains unsolved. Observations have revealed quasars, brilliant, ancient beacons powered by supermassive black holes that existed when the universe was less than 1 billion years old. These giants are millions or even billions of times the mass of the Sun, yet our models struggle to explain how they accumulated so much material in such a short time. Some theories suggest that the first black holes formed not from stars, but directly from collapsing clouds of primordial gas, creating seed. Black holes, holes large enough to grow rapidly. Others propose that early mergers or exotic processes involving dense dark matter halos accelerated their formation. Whatever the cause, their existence tells us that black holes played a crucial role in shaping the early universe, perhaps even influencing how galaxies themselves took form. And then there's the most tantalizing idea of all, that black holes could be gateways. The equations of general relativity allow for strange solutions known as wormholes, tunnels connecting distant points in space-time, or even entirely separate universes. Some theorists speculate that what we call a black hole in one universe might appear as a white hole, an object that expels matter and energy, in another. It's a breathtaking concept that every black hole could lead somewhere else, forming a cosmic network beyond our perception. Yet, as captivating as the idea is, we have no evidence it's true. The extreme conditions near the singularity would likely destroy anything that approaches it, making such journeys purely theoretical. Still, the notion that black holes might not only end worlds but also birth new ones hints at a deeper, interconnected cosmos, one where creation and destruction are two sides of the same cosmic coin. In the end, black holes are more than just voids. They are the universe's greatest teachers. Each one is a paradox wrapped in gravity, time, and mystery, silently holding the answers to the fundamental nature of reality itself. Until we can reconcile the infinite with the quantum, they will remain the darkest and most profound riddles the cosmos has ever written. From the crushing mystery of black holes, where gravity devours everything including light, we move to their smaller but equally fascinating cousins, neutron stars. If black holes are the universe's bottomless pits, neutron stars are its densest surviving remnants, teetering on the edge of collapse. They are the hearts left behind after massive stars explode as supernovae, and though they span only about 20 kilometers across, roughly the size of a city, they pack more mass than our Sun. In every way imaginable, they are nature's most extreme laboratories, where matter, magnetism, and gravity reach limits that defy comprehension. Inside a neutron star, the familiar rules of matter break apart. At its surface, atoms are stripped of their electrons, crushed into a lattice of bare nuclei. But as we move deeper, the pressure becomes so immense that even atomic nuclei dissolve. Protons and electrons merge to form neutrons, densely packed like a cosmic ocean of subatomic particles. Just a teaspoon of neutron star material would weigh billions of tons on Earth. Yet, even this description might not capture what truly happens inside. Some physicists suspect that within the very core, where densities surpass anything achievable in a lab, neutrons themselves may break down into a soup of quarks and gluons, the fundamental building blocks of all matter. Others believe there could be exotic states of matter we've never seen, such as strange quark matter, where entire regions are filled with particles that shouldn't exist in normal conditions. If we could somehow peer inside a neutron star, we might glimpse physics that no experiment on Earth could ever reproduce. Among neutron stars, a special class stands out for their rhythmic, lighthouse-like flashes, pulsars. These incredible objects emit powerful beams of radio waves from their magnetic poles, and as they spin, often hundreds of times per second, those beams sweep across space like a cosmic strobe. When one happens to align with Earth, we detect a pulse of radio energy that repeats with astonishing regularity. The first pulsar, discovered in 1967 by Jocelyn Bell Burnell, was so perfectly timed that scientists briefly wondered if it might be a signal from intelligent life. We now know these pulses come from rotating neutron stars, whose strong magnetic fields channel charged particles into beams of radiation. What remains a mystery, however, is the exact mechanism that powers these emissions. How magnetic fields and particle acceleration combine to produce such consistent, high-energy bursts that can travel across the galaxy without fading. Even more extreme are magnetars, the most magnetic objects known in the universe. Their magnetic fields are 1,000 trillion times stronger than Earth's. So intense that if one were as close as the Moon, it could erase every credit card and wipe every electronic device on our planet. These titans are rare and short-lived, their fields twisting the star's crust and occasionally snapping with explosive results. When that happens, they release bursts of X-rays and gamma rays so powerful they can momentarily outshine entire galaxies. Scientists still don't fully understand how these magnetic fields become so enormous or how they decay over time. But magnetars offer a glimpse into the most violent magnetic phenomena nature can produce. Then there's the mystery of glitches, sudden, tiny changes in a neutron star's rotation speed. Pulsars are known for their incredible precision, yet occasionally they skip a beat. These abrupt spin-ups defy the otherwise clock-like stability of their pulses. One leading explanation is that inside the star, the neutrons behave like a superfluid, a frictionless liquid that can store rotational energy. When this internal fluid shifts or unpins from the solid crust, it transfers momentum to the outer layers, making the star momentarily spin faster. These glitches not only reveal the bizarre state of matter deep inside, but also provide one of the few observational windows into a place where physics and quantum mechanics blur together at unimaginable scales. And when two neutron stars collide, the universe trembles. These mergers are among the most catastrophic events in existence, releasing more energy in a few seconds than the Sun will produce in its entire lifetime. When they crash together, their immense gravitational fields generate ripples in space-time, gravitational waves, which can now be detected here on Earth by instruments like LIGO and Virgo. These waves carry unique signatures that tell us about the properties of the stars and the structure of matter inside them. The collisions also produce bursts of gamma rays and forge some of the universe's heaviest elements: gold, platinum, uranium, the building blocks of worlds and civilizations. In 2017, scientists witnessed such an event for the first time, confirming that many of the elements we value most were born in the fiery deaths of these stellar corpses. Yet, even after these breakthroughs, neutron stars remain enigmas. What holds them together? What truly exists at their core? And could they, under the right conditions, collapse further into black holes or even stranger forms of matter we've never imagined? Each discovery reveals new layers of complexity, as though the universe itself is challenging us to understand the boundaries between energy, gravity, and matter. From black holes that swallow all information to neutron stars that preserve it in impossibly dense forms, the cosmos shows us that death in space is never the end, only a transformation. And as we continue our journey through these stellar remnants, we realize that even the smallest stars can hold the universe's deepest secrets. From the dense and mysterious hearts of neutron stars, we now turn our gaze to something far smaller, yet far more energetic. Scattered throughout the universe are invisible bullets of energy called cosmic rays, particles that streak through space at nearly the speed of light. They are the messengers of the universe's most violent events, carrying stories from the farthest reaches of creation. Every second, trillions of them bombard Earth from all directions, passing harmlessly through our bodies, through mountains, and even through entire planets. But where these particles truly come from, and how they acquire such mind-bending energy, remains one of the greatest unsolved riddles in astrophysics. Cosmic rays are mostly made up of protons and atomic nuclei, the basic building blocks of matter, accelerated to unimaginable speeds by cataclysmic forces somewhere in the cosmos. Many of them likely originate from supernova explosions, the fiery deaths of massive stars. When a star explodes, it sends powerful shock waves rippling through space, which can act like natural particle accelerators, boosting ordinary particles to near-light velocities. Others may be born in pulsars or magnetars, where intense magnetic fields fling particles outward with staggering energy. But some cosmic rays come from even more mysterious places: active galactic nuclei, where supermassive black holes feed on surrounding gas, spewing jets of charged particles that stretch millions of light years into intergalactic space. Yet, despite these known sources, a small fraction of cosmic rays, known as ultra-high energy cosmic rays, defy explanation. These particles carry energies so immense that even our most powerful human-made accelerators, like the Large Hadron Collider, can't come close to reproducing them. The highest energy cosmic rays ever detected hit Earth's atmosphere with the equivalent energy of a fast-pitched baseball concentrated into a single subatomic particle. The question is, what could possibly accelerate something that much? Some scientists propose that they come from the violent outskirts of supermassive black holes or the aftermath of neutron star collisions. Others suspect even more exotic origins, such as the decay of hypothetical particles from the early universe or the influence of physics beyond our current understanding. The mystery deepens when we consider how these particles can travel across such vast cosmic distances. Space is not empty. It's filled with interstellar gas, magnetic fields, and radiation that should slow down or deflect charged particles. Yet ultra-high energy cosmic rays seem to traverse billions of light years, surviving long enough to reach our planet. According to current physics, there's a theoretical limit, the GZK cutoff, beyond which cosmic rays should lose energy as they collide with photons from the cosmic microwave background. But some observed particles exceed that limit, implying either that our understanding of cosmic distances and interactions is incomplete, or that these rays are born far closer to us in ways we've yet to identify. When they finally strike Earth, cosmic rays interact with the upper atmosphere, triggering massive particle showers, cascades of secondary particles that spread out across kilometers. These interactions are how scientists detect them, using giant observatories like the Pierre Auger Observatory in Argentina or the Telescope Array in Utah. However, Earth's magnetic field complicates this detection. Because cosmic rays are charged, their paths are bent and twisted as they approach our planet, obscuring their original directions. It's as if we can see the arrows, but not the arches. We know they've arrived, but tracing them back to their source is nearly impossible. Only the most energetic cosmic rays, whose trajectories are less influenced by magnetic fields, offer faint clues about their origins. Despite this challenge, cosmic rays have taught us a great deal about the violence and energy of the universe. They tell us that the cosmos is far from quiet. It is alive with collisions, explosions, and forces beyond comprehension. When a neutron star collides with another, when a black hole devours a star, or when a galaxy's core unleashes a jet of plasma into space, those cataclysms send out invisible ripples that we detect as high-energy particles centuries or millennia later. In that sense, cosmic rays are time travelers, fragments of ancient events, carrying the signatures of distant worlds and forgotten cosmic cataclysms. But even now, their ultimate story remains incomplete. What powers the most extreme of these particles? Do they come from phenomena we've already discovered, or from something entirely new, perhaps even beyond the visible universe? With every detection, we get a whisper from the cosmos, a message written not in light or sound, but in energy. And as we continue to chase these elusive particles through space and time, we edge closer to uncovering the universe's most violent secrets, and maybe the hidden engines that keep it alive. From the ghostly messengers of cosmic rays, our journey turns to the whispers of the universe, mysterious signals that seem to echo across space, flickering in the void like cryptic transmissions from the unknown. For over half a century, astronomers have been listening to the cosmos, tuning into the faintest radio waves, hoping to decode the language of the stars. What they've found, however, are phenomena so unpredictable and strange that even our best theories can't yet explain them. Bursts of radio energy that last mere milliseconds, signals that appear once and never again, and cosmic rhythms that drift inexplicably out of sync. Each one may hold a clue to the workings of the universe, or perhaps just perhaps, a hint of something far more extraordinary. Among the most baffling are fast radio bursts, or FRBS, sudden, incredibly powerful flashes of radio waves that last less than a blink of an eye. First discovered in 2007, FRBs release as much energy in a single millisecond as the sun emits in days. Some originate billions of light years away, meaning their signals began traveling toward us long before Earth even formed. Yet, what causes them remains one of modern astronomy's most puzzling questions. Some fast radio bursts repeat at irregular intervals, while others appear once and vanish forever, as if the universe is sending short, coded messages and then falling silent. The leading explanations include magnetars, those hypermagnetized neutron stars capable of producing immense bursts of energy, or the collisions of dense stellar remnants like neutron stars and black holes. But the chaotic nature of these signals, their uneven timing, unpredictable brightness, and vast range of distances, suggests that we still don't fully understand their origins. And though most scientists favor natural explanations, the eerie precision and intensity of some FRBS have even led a few to wonder if they could be the work of advanced civilizations using directed energy beams for interstellar communication or propulsion. Long before FRBS captured our imagination, another mysterious signal changed the way humanity thought about listening to space. In 1977, while scanning the skies with the Big Ear radio telescope in Ohio, astronomer Jerry Amon detected an unusually strong, narrow-band signal lasting just 72 seconds. It was unlike anything seen before, so perfect in frequency and intensity that Amon famously circled it on the computer printout and wrote one word beside it: "Wow." The wow signal came from a region near the constellation Sagittarius, a relatively quiet part of the sky, and it matched the expected frequency for an artificial transmission. But despite decades of searching, it was never heard again. Was it a fluke of nature, a reflection from a passing object, or a brief transmission from an unknown source far beyond our world? No one knows. Its one-time appearance continues to haunt scientists and enthusiasts alike, standing as a lonely question mark in humanity's attempt to find company in the cosmos. Beyond the wow signal, astronomers have detected other unexplained radio signals that appear to come from deep space, defying easy classification. Some are steady but unaccountable sources, while others flicker and vanish unpredictably. In 2020, for instance, a repeating radio signal was detected from a galaxy 500 million light-years away, cycling every 16 days, a pattern no known natural process should produce so regularly. Other radio bursts have appeared with strange polarization, unusual spectra, or unexplained repetition intervals, suggesting exotic astrophysical origins, or perhaps some unknown type of cosmic phenomenon we've yet to categorize. The sheer variety of these signals tells us one thing clearly: the universe is not quiet. It's constantly speaking. We just haven't learned to interpret its language yet. Even known cosmic beacons like pulsars sometimes behave in strange, unpredictable ways. These neutron stars are famous for their clock-like pulses, yet astronomers have observed irregularities that defy explanation. Sudden slowdowns, changes in pulse shape, or unexplained timing drifts that suggest something unusual is happening deep inside or around them. Some pulsars seem to switch between active and silent states, as though their engines are turning on and off. Others emit pulses that appear to echo or scatter, hinting that something is interacting with their beams between us and them, perhaps dense plasma clouds, or even unseen companions like black holes orbiting nearby. These quirks remind us that even the most consistent cosmic rhythms can hide deep mysteries beneath their steady beats. And, inevitably, all of these phenomena, from FRBS to unexplained radio bursts, raise one provocative question: could any of them be artificial? The search for extraterrestrial intelligence, or SETI, has long sought radio signals that might indicate the presence of advanced civilizations. Scientists have developed algorithms to detect patterns or frequencies unlikely to occur naturally, and sometimes what they find borders on the uncanny. Narrowband transmissions, repeating cycles, and strangely regular bursts can all resemble what an intelligent beacon might produce. Yet so far, none have been confirmed. Every candidate signal eventually fades or turns out to have a natural explanation, though never before shaking our curiosity. Still, the possibility lingers that amid the static of the universe, something, or someone, might be trying to communicate, and we just haven't learned to listen the right way yet. Each mysterious signal is both a puzzle and a promise, a reminder that we live in a universe alive with sound and motion, where even silence might hold meaning. Whether these cosmic broadcasts are the echoes of dying stars, the cries of colliding worlds, or the engineered signatures of distant minds, they remind us that the universe is far more dynamic, strange, and alive than we could ever have imagined. Leaving behind the mysterious voices of the cosmos, we turn our focus toward the countless worlds beyond our solar system. Exoplanets. In just a few decades, we've gone from wondering if other planets even existed to discovering thousands of them orbiting distant stars. These alien worlds come in every imaginable size, composition, and configuration. Some familiar, others defying every rule we thought we knew about how planets form and behave. Yet, the more we learn, the stranger the picture becomes. What we're finding out there isn't a simple reflection of our solar system. It's an entire cosmic gallery of enigmas that challenge the very foundations of planetary science. One of the most astonishing discoveries in this gallery is that some planets orbit backward, against the spin of their stars. In our solar system, all planets orbit the Sun in the same direction it rotates, a natural result of the swirling disk of gas and dust that formed everything. But astronomers have found exoplanets where this rule simply doesn't apply. In these systems, the planet's orbital path tilts at wild angles, even rotating completely opposite to the star's spin. This bizarre behavior, known as retrograde orbit, suggests that something violent may have happened after the planet's birth, perhaps a massive collision with another planet, or gravitational chaos triggered by a passing star that flipped its orbit. In some cases, the immense tidal forces between a star and its close orbiting planet could have twisted the orbit over time. Whatever the cause, these backward worlds remind us that planetary systems can be far more turbulent and unpredictable than our calm, clockwork solar system. Equally mysterious are the so-called rogue planets, worlds adrift in the darkness, orbiting no star at all. Astronomers have detected dozens of them, drifting through interstellar space like cosmic orphans. These lonely travelers could have formed normally around stars before being ejected by gravitational interactions, or they might have formed directly from collapsing clouds of gas, much like stars themselves, only smaller. Some rogue planets are as massive as Jupiter, while others may be Earth-sized, cold, dim, and wandering endlessly between the stars. What's even more astonishing is that many scientists believe they could outnumber stars in our galaxy. If that's true, the Milky Way could be teeming with hundreds of billions of worlds, unseen and unlit, drifting silently through the void. And while their surfaces would be frozen, some could still harbor subsurface oceans heated by radioactive decay or residual core warmth, perhaps even offering niches for alien life in the most unlikely of places. Then there are the planets, whose orbits defy all expectations, worlds with eccentric paths that drag them blisteringly close to their stars before flinging them far out into deep space, repeating this cycle endlessly. These extreme orbits create unimaginable conditions, enormous temperature swings from freezing cold to molten heat, and storms that rage across entire hemispheres. One such world, HD 80606b, experiences temperatures rising by hundreds of degrees in mere hours as it swoops near its star, its atmosphere expanding and reshaping under the sudden inferno. Scientists still struggle to explain how such erratic orbits form. They could be the aftermath of gravitational duels between planets or the lingering scars of near collisions that threw entire systems into chaos. Whatever their origins, these planets show that stability, the kind that made Earth habitable, may be far rarer than we once thought. Even more baffling are the hot Jupiters, massive gas giants that orbit so close to their stars that their years last only a few days. These planets shouldn't exist where they are. According to traditional models of planet formation, gas giants can only form far from their stars, where it's cold enough for gases to condense into ice and solid cores. Yet we've found hundreds of these enormous worlds hugging their stars at distances closer than Mercury is to our Sun. The leading theory is that they formed farther out and then migrated inward due to interactions with the protoplanetary disk or gravitational tugs from other planets. But how they managed to survive this violent inward journey without being torn apart remains a cosmic puzzle. Many are tidally locked, with one side forever scorched and the other eternally dark. Worlds of endless storms, supersonic winds, and burning skies. And as if one sun weren't enough, some planets orbit binary star systems, dancing between two suns like something straight out of science fiction. These Tatooine-like worlds, named after the desert planet in Star Wars, exist in delicate gravitational balance, where the combined pull of two stars can create complex, shifting environments. Some orbit both stars together in wide loops, while others circle just one star, while the second looms distantly in the sky. The big question scientists ask is whether such systems could host habitable worlds. The answer, intriguingly, appears to be yes, under the right conditions. If the stars are close enough, their combined warmth can create a stable, habitable zone where liquid water could exist. However, the light and climate on such worlds would constantly change, their skies a dance of twin sunsets and unpredictable seasons. Life, if it arose there, would have to adapt to rhythms unlike anything on Earth. Each exoplanet discovery adds a new twist to our understanding of how worlds form and evolve. The universe, it seems, is endlessly inventive, crafting planets in impossible configurations and environments we can barely imagine. Some race backward, some wander alone, and others thrive in the glow of two suns. Every one of them expands our sense of what's possible, and everyone whispers the same question. If planets this strange can exist, what else might be out there waiting to be found? After exploring the alien worlds orbiting distant stars, it's humbling to realize that our own solar system, the one we thought we understood best, is just as strange and full of mystery. Even among our familiar planets, moons, and rings, there are cosmic puzzles that defy explanation, secrets hiding in plain sight within our celestial neighborhood. The deeper we look, the clearer it becomes. The solar system isn't a model of perfect order. It's a cosmic experiment shaped by chaos, collisions, and chance. And every planet carries scars of that violent history. Take Venus, for instance, the planet often called Earth's twin because of its similar size and composition. Yet, despite these similarities, Venus spins in the opposite direction of almost every other planet in the solar system. While Earth and most others rotate counterclockwise, Venus rotates clockwise, meaning the Sun rises in the west and sets in the east. Even more bizarre, its rotation is excruciatingly slow. One day on Venus lasts longer than an entire Venusian year. Scientists have long debated how this happened. One theory suggests that Venus may have been struck by a massive object early in its history, a glancing blow that flipped its rotation. Another proposes that the planet's thick, swirling atmosphere, heavier and more dynamic than any other, might have gradually slowed and reversed its spin through tidal friction. Whatever the cause, Venus remains a world turned upside down, both literally and figuratively, hiding its secrets beneath an atmosphere of crushing pressure and acid clouds. Farther out, Uranus presents another perplexing anomaly. Unlike any other planet, Uranus spins on its side, tilted at an incredible 98 degrees, essentially rolling around the Sun like a ball instead of spinning like a top. Its poles point almost directly toward the Sun during parts of its orbit, resulting in decades of daylight followed by decades of darkness. No other planet behaves this way, and no one knows exactly why. The leading explanation is that Uranus suffered a colossal collision in its youth, possibly with a protoplanet as large as Earth, that knocked it onto its side. But recent computer models suggest the truth could be even stranger. Uranus might have once had a massive system of moons, or a dense proto-ring that destabilized it, gradually toppling the planet over millions of years. Whatever happened, it left Uranus with a bizarre magnetic field that doesn't align with its rotation, and a frigid, featureless appearance that hides a turbulent interior we've barely begun to understand. And then there's the mystery lurking at the outer edges of our solar system, the hypothetical Planet 9. Astronomers have observed that the orbits of certain distant objects in the Kuiper belt, icy bodies far beyond Neptune, appear to be clustered together in a strange pattern, as if tugged by an unseen gravitational force. The simplest explanation is that a massive unseen planet, perhaps 5 to 10 times the mass of Earth, lies far beyond Pluto, shepherding these objects with its gravity. Yet, despite years of searching, no telescope has ever detected it. Some researchers suggest that instead of a hidden planet, these orbital patterns might be caused by the collective gravitational pull of smaller icy objects acting together, a kind of distributed mass that mimics the effects of a single large body. Others believe Planet 9 could exist but be so distant and faint that it remains hidden against the background of stars. If found, it would reshape our understanding of the solar system's formation and prove that our planetary family is still incomplete. Closer to home, another enigma is unfolding before our eyes. Saturn's rings, once thought to be eternal, are slowly vanishing. Recent observations from NASA's Cassini spacecraft revealed that the rings are shedding material into Saturn's atmosphere at a surprisingly fast rate, the equivalent of thousands of tons of icy particles per second. This process, nicknamed ring rain, means the rings could disappear entirely within just 100 million years, a blink in cosmic time. That revelation changes everything we thought we knew. It suggests that Saturn's rings are young, perhaps only a few 100 million years old, formed long after the planet itself. How they formed is still a mystery. They may be the remnants of a shattered moon, torn apart by Saturn's immense gravity, or debris left over from a collision between icy bodies. Whatever their origin, their beauty may be fleeting, a temporary spectacle in the long life of the solar system. And perhaps the most surreal mystery of all lies at Saturn's North Pole, a vast hexagonal storm unlike anything else in the solar system. This six-sided jet stream, more than 30,000 kilometers across, spins with eerie precision, maintaining its geometric shape for decades. Scientists have simulated similar patterns in fluid dynamics experiments, suggesting that the hexagon may form naturally from the interaction of atmospheric currents moving at different speeds. But the stability and longevity of the storm are baffling. How does such a perfect hexagon persist in a turbulent atmosphere where everything else is chaotic and shifting? Some suspect it may be anchored deep within Saturn's internal layers, a kind of standing wave that reflects the planet's rotation. Others think it could be influenced by variations in Saturn's magnetic or heat flow. Yet, after decades of observation, it remains one of the strangest meteorological phenomena ever seen, a colossal geometric riddle swirling endlessly in the clouds. These mysteries remind us that even in our cosmic backyard, the universe refuses to be predictable. The planets we thought we knew continue to surprise us, revealing quirks and contradictions that challenge every theory we create. Venus spins backward, Uranus rolls sideways, an unseen planet may lurk in the dark, and Saturn, with its fading rings and impossible hexagon, continues to rewrite the story of how solar systems evolve. The deeper we look, the clearer it becomes that even here, close to home, the universe still keeps its most beautiful secrets just out of reach. Mars, our rust-colored neighbor, has long been humanity's mirror in the cosmos, a planet that feels tantalizingly familiar yet shrouded in mystery. It is a world that once may have been like Earth, with rivers, lakes, and perhaps even oceans, but now stands silent and desolate beneath a thin, toxic sky. Despite the countless probes, rovers, and orbiters we've sent, Mars continues to whisper secrets that science has yet to fully decode. Its barren surface is a storybook of vanished water, lost air, and fleeting hints of life, a riddle written in red dust and ancient stone. One of the greatest Martian mysteries is what happened to its atmosphere. Billions of years ago, Mars was warmer and wetter, its skies thick enough to sustain liquid water on the surface. But today, the atmosphere is so thin that it can barely support a wisp of breeze, about 1% the pressure of Earth's. Without a dense atmosphere, water can't stay liquid. It either freezes or evaporates into space. The prevailing theory is that Mars lost its atmosphere because it lost its magnetic field. Unlike Earth, whose magnetic shield protects it from solar radiation, Mars's magnetic field faded around 4 billion years ago. Without that protection, the solar wind, a stream of charged particles from the Sun, stripped away its atmosphere molecule by molecule over eons. NASA's MAVEN mission confirmed this process by detecting how solar storms continue to erode the upper atmosphere even today. But why Mars's magnetic field collapsed so early remains uncertain. Perhaps its molten core cooled too quickly, or massive impacts disrupted its internal dynamo. Either way, this loss marked the end of Mars's habitable era and the beginning of its long, cold exile. Yet, despite its apparent lifelessness, Mars still surprises us with hints that its story may not be finished. One of the most intriguing phenomena are the recurring slope lineae, dark streaks that appear seasonally on Martian hillsides and crater walls, only to fade again when winter comes. First spotted by orbiters, these streaks looked remarkably like trickles of water flowing down the slopes. At first, scientists thought they might be caused by briny, salty water that could briefly exist in the thin Martian atmosphere. Later studies complicated that theory. The streaks might instead be caused by shifting sand or dust, or by sublimation, the direct evaporation of ice into vapor. Still, no one knows for sure. If even trace amounts of liquid water exist on Mars today, it would be a game changer for our understanding of potential Martian life, and for our future there. Adding to the intrigue are the methane spikes detected in Mars's atmosphere. Methane on Earth is often produced by biological activity, such as microbes, though it can also come from geological processes. When NASA's Curiosity rover detected fluctuating levels of methane in Gale Crater, it sparked worldwide excitement and debate. The spikes appeared and disappeared unpredictably, suggesting that something active on or beneath the surface is releasing the gas. Yet when the European Space Agency's ExoMars Trace gas orbiter tried to measure it, it found nothing, leading to a baffling contradiction. Where does the methane come from, and why does it vanish so quickly? Could it be destroyed by unknown chemical reactions in the Martian atmosphere, or trapped in the soil, releasing only occasionally? Or could it, as some dare to hope, hint at microbial life deep underground, still clinging to existence beneath the cold surface? Mars's ancient landscape tells an even deeper story, one of flowing rivers, vast lakes, and vanished oceans. Satellite imagery reveals dry riverbeds winding for hundreds of kilometers, delta formations, and mineral deposits that could only have formed in standing water. There's overwhelming evidence that billions of years ago, Mars had enough water to cover the planet in a global ocean hundreds of meters deep. So where did all that water go? Some of it likely escaped into space along with the atmosphere, while some froze into the polar ice caps or became locked in underground permafrost. Recent radar studies suggest vast reserves of frozen or even liquid water might still exist beneath the surface, hidden aquifers trapped beneath layers of ice and rock. Understanding what happened to that water is key to understanding how Mars transformed from a potentially habitable world into a frozen desert. And that leads us to the question that has haunted scientists and dreamers for generations. Could life still exist on Mars today, though the surface is bombarded by radiation and frozen solid? Beneath the ground lies a different story. Deep underground, temperatures rise, and liquid water may still persist in isolated pockets, creating potential refuges for microbial life. On Earth, we've found hardy microbes, extremophiles, thriving in places once thought impossible, from the icy depths of Antarctica to the radioactive cores of reactors. If life ever arose on Mars, it may have retreated underground to survive, waiting patiently in the dark for billions of years. Upcoming missions, like ESA's Rosalind Franklin rover and NASA's Sample Return program, aim to search for direct signs, fossilized microbes, chemical signatures, or living organisms hidden in subsurface soil. If even one living cell were found, it would prove that life isn't unique to Earth, that it's a natural outcome of cosmic chemistry wherever the conditions allow. Mars remains a planet of echoes, echoes of water, air, and perhaps life. Every mission sent there uncovers new puzzles, methane that flickers in and out of existence, streaks that come and go with the seasons, magnetic scars of a lost atmosphere. It is a world that seems to hover forever between past and present, between death and possibility. And though it now sleeps beneath a frozen sky, Mars continues to beckon, not just as a destination for explorers, but as a mirror for our own planet's fragile fate. As we leave the dusty plains of Mars behind, our journey returns homeward, to the luminous companion that has watched over Earth for billions of years, the Moon. It is our closest neighbor, a silent guardian that tugs at our tides, stabilizes our planet's tilt, and lights up our nights. Humanity has walked upon its surface, mapped its craters, and brought back its rocks. Yet, despite all this familiarity, the Moon remains profoundly mysterious. Beneath its quiet glow lie questions about its birth, its inner workings, and its hidden dynamism that still challenge modern science. The Moon, it seems, is not as dead or as simple as we once believed. The greatest of these enigmas begins with its origin. The most widely accepted explanation, the giant impact hypothesis, proposes that around 4.5 billion years ago, a Mars-sized body called Theia collided with the early Earth. The impact blasted enormous amounts of molten debris into orbit, which eventually coalesced into the Moon. This theory elegantly explains the Moon's composition, which is strikingly similar to Earth's outer layers, as well as its angular momentum and size. Yet, it's not a perfect fit. Lunar samples brought back by Apollo astronauts show oxygen isotopes nearly identical to those of Earth. Too identical, perhaps. If the Moon formed from a mix of Earth and Theia's materials, scientists would expect subtle differences. Some researchers propose that the impact was so violent it vaporized both bodies, mixing their elements completely. Others suggest alternate ideas, such as the Moon forming alongside Earth from the same primordial cloud, or multiple smaller impacts combining over time. Whatever the case, the Moon's birth remains one of the most dramatic and uncertain chapters in the solar system's story. But the Moon's mysteries don't end with its formation. Despite being thought of as geologically dead, it still trembles, quite literally. Instruments left behind by Apollo missions detected moonquakes, some strong enough to have startled the astronauts had they been standing on the surface. These quakes come in several forms: shallow ones that occur near the surface, deep quakes that rumble hundreds of kilometers below, and thermal quakes caused by the Moon's crust expanding and contracting as it transitions from day to night. What's most puzzling are the deep quakes. They occur at regular intervals, hinting at tidal forces from Earth's gravity as the likely trigger. But the shallow quakes are far more mysterious. Some have registered magnitudes up to 5.5 on the Richter scale, strong enough to damage structures if they occurred on Earth. These could indicate that the Moon's crust is still shifting, cracking, or settling, suggesting it may not be as geologically inactive as we once thought. And then there are the transient lunar phenomena, or TLPS, strange fleeting flashes of light, glowing patches, and color changes reported on the Moon's surface for centuries. Astronomers from the 1600s to the present have documented these events, describing brief red glows, bluish flares, or mist-like hazes lasting from seconds to hours. Even modern telescopes occasionally record unexplained bursts of light or local brightening in certain regions, especially near active geological areas like the Aristarchus crater. Scientists have proposed several explanations: meteoroid impacts releasing dust and gas, electrical discharges from charged particles, or outgassing, the sudden release of trapped gases from the Moon's interior. But none fully explain the variety or frequency of these events. If the Moon is still venting gases or experiencing minor eruptions, it would mean that some part of its interior remains active, a haunting reminder that our celestial neighbor may still be alive beneath its tranquil surface. Adding to the Moon's mystery is the stark contrast between its near side, the face we always see, and its far side, which remained hidden until the space age. The near side is marked by vast dark plains known as maria, ancient lava flows that give the Moon its familiar patterns. The far side, however, is almost entirely cratered, with a thicker crust and far fewer maria. Why the two hemispheres are so different remains one of lunar science's biggest puzzles. One leading theory is that the far side's crust is thicker because of uneven heat distribution in the Moon's early history. Radioactive elements concentrated on the near side may have kept it warmer, allowing volcanic activity to resurface that half while leaving the far side frozen and rugged. Another theory suggests a second moon once orbited Earth and eventually merged with the current one, plastering one hemisphere with extra crust. Whatever the truth, the Moon's two faces seem to tell two entirely different stories, one of fiery youth, the other of ancient stillness. Finally, there's the question of whether the Moon's interior is still geologically active. For decades, scientists assumed it had gone cold, its small size and lack of atmosphere seemingly dooming it to stillness. But recent evidence paints a different picture. Data from NASA's Lunar Reconnaissance Orbiter show young fault lines and ridges, so fresh that they could have formed within the last 50 million years, perhaps even more recently. Some quakes recorded by Apollo appear to have originated near these faults, implying ongoing tectonic activity. Even more intriguing, traces of gas emissions and localized heating suggest residual volcanic or thermal processes could still be occurring beneath the surface. While not active like Earth, the Moon may be geologically restless, its interior slowly cooling and contracting even now. All these clues, the unexplained flashes, the deep rumblings, the asymmetry of its face, remind us that the Moon is far more than a silent companion. It is a dynamic relic of the early solar system, still evolving, still holding secrets beneath its dusty crust. We've walked upon it, studied its rocks, and mapped its craters. But we have not yet unraveled its soul. The Moon remains what it has always been, a bridge between Earth and the cosmos, quietly keeping the mysteries of creation within reach, yet always just beyond our grasp. After gazing at the silent mystery of the Moon, our attention turns to the blazing heart of our solar system, the Sun, the life-giver and destroyer, the fiery engine that sustains every living thing on Earth. We take it for granted as the steady light in our sky, but in truth, the Sun is one of the most complex and least understood objects in all of astrophysics. It's not just a glowing ball of fire, it's a churning, magnetic, ever-changing star whose inner workings are still full of unanswered questions. Even after centuries of observation, the Sun continues to defy prediction, erupting, pulsing, and fluctuating in ways that science is only beginning to understand. Perhaps the most confounding mystery of all lies in the temperature of the Sun's atmosphere. At its surface, the photosphere, the Sun burns at around 5,500 degrees Celsius. But move outward into its outer atmosphere, the corona, and the temperature inexplicably skyrockets to over 1,000,000 degrees. This makes no sense according to classical physics. How can the outer layers be hundreds of times hotter than the surface below them? It's as if standing away from a fire made you hotter than standing in its flames. Scientists believe that magnetic fields hold the key. The Sun's surface is a chaotic tangle of magnetic loops, constantly twisting, reconnecting, and snapping like rubber bands. These violent interactions may fling energy into the corona in the form of waves or particles, heating it from above in a process known as magnetic reconnection. Yet, despite missions like NASA's Parker Solar Probe flying closer to the Sun than ever before, we still don't fully understand how these mechanisms work or why they're so efficient. The corona's mystery remains one of the most baffling paradoxes in astrophysics, a puzzle that defies the simple laws of thermodynamics. Just as puzzling are the patterns in the Sun's magnetic cycle. Every 11 years or so, the Sun undergoes a dramatic transformation known as the solar cycle, when its magnetic poles flip. North becomes south, and vice versa. During this period, the Sun's activity surges. Dark sunspots multiply, massive solar flares erupt, and streams of charged particles pour into space. These cycles influence space weather, affecting satellites, power grids, and even Earth's climate. But why the cycle lasts about 11 years, and what precisely drives it, remains unclear. The Sun's magnetic field is generated by a solar dynamo, the motion of hot plasma deep within its layers. But modeling this dynamo has proven incredibly difficult. Sometimes the Sun's cycles weaken or intensify without warning, leading to mysterious grand minima, like the Maunder minimum in the 1600s, when sunspots nearly disappeared for decades. Was that a natural lull, or a deeper fluctuation in the Sun's internal structure? We still don't know, The sun's rhythm is one of nature's most intricate clocks, one that occasionally skips a beat. Then come the solar flares, colossal explosions of energy that erupt from the sun's surface, hurling billions of tons of plasma into space. These events can release as much energy as billions of hydrogen bombs in seconds. The largest flares can cause coronal mass ejections, CMES, storms so powerful they can knock out satellites and electrical grids on Earth. We know that flares are triggered by magnetic fields snapping and reconnecting. But what initiates that snap, the precise trigger that causes a region to suddenly unleash its pent-up energy, remains uncertain. Even with advanced solar observatories like NASA's Solar Dynamics Observatory and the ESA's Solar Orbiter, scientists struggle to predict when and where a flare will occur. It's as if the sun's surface operates under rules we don't yet understand, storing tension invisibly before unleashing chaos without warning. Some researchers suspect that small-scale processes deep below the surface, nanoflares or turbulent plasma flows, could be the hidden catalysts. For now, predicting a solar flare remains as much art as science. The sun also bathes the solar system in a continuous stream of charged particles known as the solar wind. This wind shapes the boundaries of our solar system and drives the magnificent auroras that shimmer near Earth's poles. Yet, it behaves in ways that are still deeply mysterious. Sometimes the solar wind blows gently, while at other times it surges with ferocity, carrying bursts of radiation that can disrupt communications and endanger astronauts. The variation in its intensity and structure is far more dramatic than models predict. The solar wind appears to come from open regions of the sun's magnetic field, known as coronal holes, but how these streams accelerate to supersonic speeds remains unclear. Parker Solar Probe has observed strange magnetic switchbacks, zigzag patterns in the solar wind that may be tied to the sun's rotation or hidden magnetic turbulence. Understanding this wind isn't just a matter of curiosity. It's essential for protecting our planet and spacecraft from the sun's unpredictable moods. And finally, we face the question that has haunted humanity since we first looked at the sky. What will happen when the sun dies? Like all stars, the sun is a finite engine. It has been burning hydrogen into helium for about 4.6 billion years and has enough fuel to last another 5 billion or so. When that fuel begins to run out, the balance that keeps the sun stable will collapse. Its core will contract, heating up, while its outer layers expand into a colossal red giant, swallowing Mercury and Venus, and possibly Earth itself. For a time, the sun will glow as a vast dying ember, its radius extending beyond the orbit of our planet. Then, it will shed its outer layers into space, creating a stunning planetary nebula, a glowing shell of gas and dust illuminated by the fading remnant at its center. That remnant will shrink into a white dwarf, a dense, Earth-sized ember glowing with the last residual heat of billions of years. Over unimaginable spans of time, even that will fade into darkness, becoming a cold, black dwarf, the silent tombstone of a star that once gave life. Yet, the sun's death will not be an end, but a transformation. The elements it forges and releases, carbon, oxygen, and nitrogen, will seed future stars and planets. In a way, every breath we take is already a gift from ancient suns that lived and died before ours. The sun's mysteries, from its fiery corona to its ultimate fate, remind us that even the most familiar star is full of wonder, and that in the cycles of light and darkness, creation and destruction, the universe endlessly renews itself. From the burning brilliance of the sun, our gaze drifts outward once more, into the strange and beautiful realms of the planets themselves. Each world in our solar system tells a different story of creation, violence, and change. Yet beyond their familiar appearances lies a treasure trove of planetary phenomena so bizarre that even our most advanced science can only speculate about their causes. Here, storms rage for centuries, diamonds fall like rain, and icy moons conceal oceans that may be alive. The solar system, far from being static, is a living laboratory of the extraordinary. Let's begin in the deep, cold reaches of Uranus and Neptune, the ice giants at the edge of our system. Hidden beneath their blue-green clouds, scientists believe that diamonds literally rain from the sky. These planets are composed largely of hydrogen, helium, water, ammonia, and methane, the last of which plays a critical role in this glittering phenomenon. Deep inside, under immense pressure and scorching heat, methane molecules can break apart, releasing carbon atoms. These atoms compress into crystalline structures, diamonds, that then fall like solid rain toward the core. Laboratory experiments have recreated this process, compressing methane with laser shocks and watching it form nanodiamonds in real time. It's possible that entire layers of diamond sludge or even diamond oceans exist within Neptune's interior, glimmering unseen beneath the clouds. If true, these worlds may be home to more jewels than all of Earth combined, but locked away forever in a pressure so immense that no probe could survive long enough to witness it. Traveling inward, we arrive at the colossal world of Jupiter, where one of the most mysterious and iconic features in the solar system resides, the Great Red Spot. This monstrous storm, larger than Earth itself, has raged for at least 350 years, possibly much longer. How can a storm persist for centuries when even Earth's most powerful hurricanes fade in weeks? The answer, scientists believe, lies in Jupiter's unique atmosphere. With no solid surface to absorb energy, storms can churn endlessly, feeding on deeper jet streams that circulate through the planet's layers. The red spot may draw strength from heat rising within Jupiter's interior, trapped and amplified by surrounding wind currents. Yet, despite centuries of observation, no one fully understands why the storm is shrinking, it's been slowly contracting for decades, or why it remains red. Some researchers suggest that complex organic molecules, phosphorus compounds, or ultraviolet radiation interacting with ammonia might give the storm its crimson hue. But the truth is still elusive, buried within the turbulent depths of the gas giant. Closer to the Sun lies Mercury, small, scorched, and yet strangely dense. So dense, in fact, that more than half of its volume is made up of metallic core. This makes it one of the most metal-rich objects in the solar system. The question is, why? One theory suggests that in the early days of the solar system, Mercury was much larger, but suffered a catastrophic collision with another protoplanet. The impact stripped away much of its outer rocky mantle, leaving behind a core-dominated world. Another theory posits that intense solar radiation early in the Sun's life vaporized lighter materials from Mercury's surface, leaving behind only the heaviest elements. Even today, its magnetic field, surprisingly strong for such a small planet, hints at a molten outer core still in motion. Mercury is a survivor, the ancient remnant of violent beginnings that nearly tore it apart, but never quite did. Then we turn to Venus, Earth's twisted twin, similar in size and mass, yet transformed into a hellish furnace. Venus's surface temperature exceeds 460 degrees Celsius, hot enough to melt lead, and its atmosphere is thick with carbon dioxide and sulfuric acid clouds. But Venus may not have always been this way. Evidence suggests it once had oceans and a milder climate, perhaps even conditions suitable for life. So what went wrong? The culprit is a runaway greenhouse effect. At some point, volcanic activity released vast amounts of carbon dioxide into the atmosphere. As greenhouse gases trapped more heat, the planet's oceans began to evaporate, adding water vapor, itself a potent greenhouse gas, to the cycle. With no way to regulate its temperature, Venus spiraled into an irreversible feedback loop, boiling away its seas and baking its surface beneath crushing pressure. Today, its atmosphere serves as a cautionary tale, a vision of what can happen when climate spirals beyond balance, and the forces that once nurtured a world turn against it. And finally, far beyond Saturn, in the icy darkness, lies one of the most mysterious worlds of all, Enceladus, a tiny moon with a secret. Beneath its frozen crust lies a vast subsurface ocean, kept warm by gravitational tides from Saturn's immense pull. Through cracks near its south pole, Enceladus erupts with towering plumes of water vapor, ice, and organic compounds, shooting hundreds of kilometers into space. When NASA's Cassini spacecraft flew through these plumes, it found complex organic molecules, salts, and even hints of hydrothermal activity, the same kind of environment that, on Earth, teems with microbial life around deep-sea vents. What powers these eruptions remains a matter of debate. The most likely explanation is that heat generated by the constant flexing of Enceladus's interior due to Saturn's gravity melts its icy mantle, creating pockets of liquid that escape through fissures. Yet, the sheer vigor and consistency of these plumes suggest that something dynamic, perhaps a global ocean in motion, lies beneath the ice. Enceladus, once thought to be an insignificant moon, may now be one of the most promising places in the solar system to search for life. From diamond storms to eternal tempests, from molten hearts to frozen oceans, the planets and moons of our solar system reveal nature's limitless creativity. Each one defies expectation, turning science into wonder and wonder into mystery. And if even these nearby worlds hold such strange secrets, how many more unimaginable phenomena must await us in the countless planetary systems scattered across the galaxy? From the intimate scale of planets and moons, we now step back, far back, to glimpse the grand design of the cosmos itself. When astronomers map the universe on its largest scales, a breathtaking structure emerges. Galaxies are not scattered randomly like cosmic confetti, but instead form a vast, interconnected web stretching across billions of light years. Between these luminous threads lie immense voids of darkness, regions so empty they challenge our understanding of how matter is distributed. These patterns, the filaments, clusters, and mysterious forces at play, form the skeleton of the universe, a cosmic architecture shaped by gravity, dark matter, and perhaps by laws we still don't fully comprehend. Among the most haunting features of this grand design are the cosmic voids, enormous regions of near-nothingness spanning tens to hundreds of millions of light-years. Within these voids, there are almost no galaxies, no clusters, and in some cases, barely any detectable matter at all. The Boötes void, one of the largest known, is so vast that if our Milky Way were placed at its center, we wouldn't see another galaxy for hundreds of millions of light years in any direction. These voids make up most of the universe's volume, yet we know little about them. Are they truly empty, or do they contain faint, undetectable structures? Dark galaxies, or low-density dark matter filaments that our instruments can't yet see. Some researchers propose that the voids may act as cosmic laboratories for dark energy, where the universe's accelerated expansion plays out most dramatically. They may also hold clues to how matter first clumped together after the Big Bang, leaving behind the vast gaps we see today. As we map the movements of galaxies, we discover another enigma, a mysterious gravitational pull known as the Great Attractor. Located roughly 150 to 250 million light-years away in the direction of the Centaurus constellation, This unseen concentration of mass appears to be tugging on our entire region of the universe. The Milky Way, along with thousands of neighboring galaxies, is moving toward it at over 600 kilometers per second. But what exactly is causing this pull remains unclear. The problem is that much of the Great Attractor lies hidden behind the dense plane of our own galaxy, obscured by dust and stars, a region astronomers call the zone of avoidance. Some theories suggest it could be a massive supercluster of galaxies, perhaps part of the even larger Laniakea supercluster, the vast cosmic region to which our Milky Way belongs. Others propose that its gravitational influence may come from unseen dark matter concentrations. There's even speculation that what we perceive as the Great Attractor could be an illusion, a side effect of cosmic flows shaped by the expansion of space itself. Whatever it is, something immense and unseen is pulling us, and the entire local group of galaxies, toward a point in space we still cannot fully observe. Yet, the universe's oddities don't stop at gravity. Across distances so vast they defy comprehension, astronomers have found unexpected alignments in the light of distant quasars, the hyper-bright cores of galaxies powered by supermassive black holes. Observations suggest that the spin axes of these quasars, separated by billions of light-years, appear to point in similar directions. Statistically, such alignment shouldn't exist. Each quasar should be randomly oriented, like galaxies scattered in all directions. But this cosmic synchronicity hints that something larger may be at work. Perhaps a vast magnetic field, relic cosmic rotation, or even a fundamental property of space-time itself, influencing how matter organizes on the larger scales. If confirmed, this alignment could mean that the universe isn't entirely isotropic, that it may have a subtle preferred direction, a cosmic axis that challenges the long-held assumption that the universe looks the same in every direction. This idea ties directly into one of the most beautiful and puzzling discoveries of modern cosmology, the cosmic web. On enormous scales, galaxies are arranged not as isolated dots, but as filaments, colossal threads of matter connecting clusters across the universe. Between them lie the great voids, forming a vast, sponge-like pattern. These filaments are made primarily of dark matter, whose invisible gravity sculpted the luminous matter, stars, gas, and galaxies that we can see. The web extends across billions of light-years, resembling the neural structure of a brain or the root system of a cosmic organism. Simulations suggest that after the Big Bang, slight density fluctuations in the early universe caused matter to collapse under gravity, stretching into these interconnected strands. Yet, we still don't know why this large-scale structure is so orderly or why it has such self-similar patterns at different scales, from the clustering of galaxies to the arrangement of superclusters. Could it be that the universe itself is following a deeper, fractal geometry, one that reflects underlying physical laws beyond our current understanding? These vast patterns lead to one final, unsettling question. Does the universe have a preferred direction or structure? For decades, cosmologists have worked under the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales. But emerging evidence hints that this might not be entirely true. The so-called axis of evil, a strange alignment observed in the cosmic microwave background radiation, appears to stretch across the sky, challenging the assumption of randomness. Combined with the quasar alignments and large-scale cosmic flows, it raises the possibility that the universe could have a kind of cosmic north and south, a directional imprint left over from the earliest moments after the Big Bang. If that's true, it could force a profound revision of our cosmological models, suggesting that the universe, far from being an impartial expanse, might have inherent asymmetries woven into its very fabric. From the yawning emptiness of cosmic voids to the hidden forces tugging on entire galaxies, from the filaments that bind the universe like a web to the possibility of a cosmic axis guiding its evolution, we see that the universe's structure is not random chaos, but an intricate, almost purposeful tapestry. Each discovery brings us closer to understanding the grand architecture of existence, and each answer opens new questions about what, if anything, lies beyond the cosmic horizon. As we leave behind the vast scaffolding of the universe, its filaments, voids, and hidden gravitational pulls, we move into a realm even more subtle yet equally perplexing: the anomalies of light and energy that ripple through the cosmos. Light is our greatest tool in exploring the universe, carrying with it the stories of stars, galaxies, and cosmic events across billions of years. Yet, time and again, it reveals inconsistencies, flickers and surges that defy our understanding of physics. Energy, the fundamental currency of existence, often refuses to balance the cosmic books. These mysteries in light and radiation challenge everything from the nature of dark matter to the very limits of the observable universe, suggesting that something deeper and stranger may be shaping what we see. Astronomers have long been puzzled by why some galaxies appear far brighter than they should be. Based on known laws of physics, the brightness of a galaxy depends on the number of its stars, their ages, and how much dust and gas it contains. Yet, certain galaxies, especially those in the early universe, shine with an intensity that shouldn't be possible given their age. Observations from telescopes like Hubble and James Webb have revealed ancient galaxies glowing far more brightly than models predict, as if their stars formed in furious bursts of activity immediately after the Big Bang. This excess luminosity could mean that early galaxies were far more efficient at forming stars, or that new physics, perhaps exotic dark matter interactions or unknown feedback processes, amplified their light. Some even speculate that what we see might be gravitational lensing, where massive foreground objects magnify the light of distant galaxies like cosmic magnifying glasses. Still, not all bright anomalies can be explained this way. The universe's first billion years remain a time of unexpected brilliance, an era where galaxies seem to have ignited faster and fiercer than theory allows. Beyond the glow of galaxies, scientists have discovered something even stranger: a massive, unexplained movement of entire galaxy clusters, known as the dark flow. In 2008, researchers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe, WMAP, found that vast numbers of galaxy clusters appeared to be drifting together in one direction, as if being pulled by something beyond the observable universe. This motion, which spans hundreds of millions of light years, cannot be explained by cosmic expansion or known gravitational structures. Some cosmologists propose that the dark flow could be caused by the gravitational pull of structures beyond our visible horizon, perhaps other universes or massive regions of warped space-time left over from cosmic inflation. Others argue that the effect may be an illusion caused by data noise or unaccounted systematics in our observations. Yet, even after newer missions like Planck refined our measurements, the dark flow remains a controversial but tantalizing hint that the universe might be influenced by forces or realms that we cannot yet see. Then there are the most violent flashes of light known to science: gamma-ray bursts, GRBS. These cosmic explosions release in seconds more energy than the Sun will emit in its entire lifetime, outshining all other sources in the universe while they last. Some gamma-ray bursts are linked to the collapse of massive stars into black holes, while others arise from the collisions of neutron stars. But not all fit neatly into these categories. A few bursts exhibit strange timing, irregular afterglows, or spectra that don't match any known mechanism. Some appear to come from regions with no obvious host galaxy at all, leading to speculation that they might originate from entirely new types of astrophysical phenomena, or even from events involving exotic physics, such as the evaporation of primordial black holes or the decay of hypothetical dark matter particles. Whatever their origins, gamma-ray bursts are not just explosions. They're cosmic beacons, flashing across time and space, reminding us that the universe is capable of energies we can barely comprehend. Even individual stars have joined the list of celestial enigmas. One of the most famous cases is Tabby's star, officially KYC 84622852, which gained attention in 2015 when astronomers noticed it dimming in irregular, dramatic ways. At times, the star's brightness dropped by as much as 20%, then brightened again without any predictable pattern. No known natural cause could explain the complexity of its light curve. Initially, some speculated it might be surrounded by a vast cloud of dust or debris, perhaps from a shattered planet or a collapsing ring system. Others suggested comet swarms or irregular planetary transits. And yes, for a brief, thrilling moment, a few even entertained the idea of a megastructure, a vast artificial construction such as a Dyson sphere partially blocking the star's light. Later studies showed that dust was the most likely culprit, but the exact mechanism remains uncertain. And Tabby's star isn't alone. Similar dimming stars have since been discovered, each challenging our understanding of stellar behavior. These cosmic flickers remind us that even familiar stars can behave in ways that hint at hidden processes, or perhaps hidden presences. But perhaps the most haunting anomaly of all lies not in stars or galaxies, but in the cosmic microwave background, CMB, the faint afterglow of the Big Bang itself. The CMB is the oldest light in the universe, a near-uniform field of radiation stretching across all of space, slightly rippled by the density variations that seeded galaxies. Yet, when scientists measure its energy distribution, something doesn't quite add up. There appears to be unaccounted energy, subtle irregularities in temperature and polarization that standard cosmological models struggle to explain. Some regions of the CMB, like the infamous cold spot, are far larger and colder than they should be, leading some to speculate about the presence of massive voids, defects in space-time, or even imprints of other universes brushing against our own. The overall energy density of the CMB also leaves open questions about dark matter, dark energy, and the possibility of unknown forces that shaped the universe's earliest moments. These tiny fluctuations, barely measurable, may hold the keys to everything, from the origins of structure to the fate of the cosmos itself. All these anomalies, galaxies that shine too brightly, clusters that drift toward unseen attractors, bursts of light that outpace physics, stars that flicker without reason, and background radiation that refuses to fit the model, paint a picture of a universe still full of surprises. The deeper we look, the more we find cracks in our understanding, faint glimmers of something larger and more intricate behind the cosmic curtain. Light, for all its clarity, often reveals mystery rather than certainty, a reminder that even the oldest, brightest truths of the universe still shimmer with unanswered questions. From the riddles of light and energy, we step into a domain where science begins to bend, and reality itself starts to blur, the mysteries of time and relativity. Time is the most familiar thing in our lives, yet perhaps the least understood. It governs every heartbeat, every orbit, every star's rise and fall. But in the cosmic arena, time doesn't flow with the steady rhythm we perceive. It stretches, twists, and even halts altogether under the influence of gravity and motion. Einstein's theory of relativity revealed that time is not an absolute constant, but a dimension, one woven together with space itself into the fabric of the universe. Yet, even that profound understanding is only the beginning. When we push deeper into the extremes of physics, near black holes, through wormholes, or down to the quantum scale, time becomes an illusion, a paradox, and perhaps the universe's most profound secret. At the very edge of understanding lies the singularity, the heart of a black hole, where gravity crushes everything, including space and time, into a single point of infinite density. According to general relativity, the laws of physics break down completely there. The curvature of space-time becomes so extreme that all paths forward lead to a single conclusion: time stops. For an outside observer, anything falling toward a black hole appears to slow down endlessly, frozen at the event horizon. But for the object itself, time continues normally until it reaches the singularity, where it ceases to exist as we understand it. This contradiction reveals a terrifying and beautiful truth. Time is not universal. It is personal, local, and relative to each observer. Yet what truly happens at that central point, where the equations of relativity collapse, remains one of the deepest mysteries in science. Some theorists propose that quantum mechanics might smear out the singularity, replacing it with a finite region of extreme energy called a Planck core. Others speculate that the singularity could be a bridge, a passage to another universe. But until we find a theory that unites quantum physics and gravity, what lies beyond that gravitational curtain will remain forever hidden. That same concept of a bridge through space-time brings us to one of the most tantalizing possibilities in theoretical physics: wormholes. Sometimes called Einstein-Rosen bridges, wormholes are hypothetical tunnels that connect two distant regions of space, and possibly even two different universes. If such a structure existed, traveling through it could, in theory, allow instantaneous movement across vast distances or even through time itself. The mathematics of general relativity allows for wormholes, but reality may not. For a wormhole to stay open, it would need to be stabilized by exotic matter, a material with negative energy density that counteracts gravity's pull. So far, no such material has been found, and even if it exists, keeping a wormhole stable long enough for travel might be impossible. Still, wormholes remain one of the most captivating ideas in physics, inspiring both scientific exploration and imagination. They serve as reminders that our universe's geometry could be far stranger and more interconnected than we can perceive. This, naturally, leads to a question that has haunted dreamers and scientists alike. Is time travel possible? According to relativity, the answer, surprisingly, is yes, though only in certain directions and conditions. Time travel to the future is not only possible, it's already been proven. When an object moves at speeds close to light, time slows down for it relative to an outside observer, an effect known as time dilation. Astronauts on the International Space Station, for example, age milliseconds less than people on Earth due to their speed and weaker gravity. In extreme cases, near black holes or through rapid acceleration, time could slow so dramatically that a traveler might leap centuries ahead while only aging moments themselves. Traveling backward in time, however, presents deeper paradoxes. Some solutions to Einstein's equations, like rotating black holes, cosmic strings, or traversable wormholes, theoretically allow closed time-like curves, loops where time folds back on itself. But these scenarios also invite impossible contradictions: the grandfather paradox, causality violations, and inconsistencies that reality itself seems to forbid. Many physicists believe that some yet unknown law of quantum gravity prevents backward time travel entirely, preserving the consistency of the universe. Yet, as long as the mathematics allows for it, the door to the past remains cracked, even if only in theory. Even within the familiar framework of relativity, time moves differently in gravitational fields. The stronger the gravity, the slower time flows. This is not just theory, it's measurable fact. In 2010, scientists placed two atomic clocks just 33 centimeters apart at different heights on Earth, and found that the lower one, being closer to the planet's center of gravity, ticked slightly slower. Near a massive body like a black hole, the effect becomes extreme. A few minutes spent near its edge could correspond to years passing in distant space, a phenomenon beautifully depicted in science and film alike. This gravitational time dilation not only reshapes our understanding of physics, but forces us to rethink existence itself. In the universe's deepest wells of gravity, time and space are not separate. They are fluid, malleable, and dependent on perspective. The implication is staggering. There is no single now. Each point in the universe experiences its own version of time, its own rhythm in the cosmic symphony. But if relativity twists time, quantum mechanics nearly dissolves it altogether. In the quantum world, where particles can exist in multiple states at once, the flow of time seems to lose its meaning. Equations describing quantum systems, like the Schrödinger equation, treat time as an external parameter, not something that emerges from the system itself. Yet, in theories attempting to merge quantum physics with gravity, time often disappears entirely. In the Wheeler-DeWitt equation, a proposed model for the quantum state of the entire universe, there is no time variable at all, suggesting that time might not be fundamental, but an emergent illusion arising from change and interaction. This radical idea implies that what we perceive as the passage of time might be a byproduct of consciousness or entropy, a way for the universe to measure the difference between before and after. Some physicists even propose that time could run in both directions at the quantum level, with the arrow of time emerging only when complexity and thermodynamics take hold. In the end, time remains the ultimate cosmic riddle, a dimension, a flow, a perception, and perhaps an illusion. Relativity shows us that it bends. Quantum mechanics hints that it may not exist at all. Somewhere between these two extremes lies the truth, a theory of everything that can explain how time, space, and matter emerge from the same fundamental fabric. Until then, we live caught in time's current, moving forward through a universe that may not have a true before or after, only an eternal, infinite now unfolding in countless ways across the stars. From the strange bending of time and the hidden laws that govern existence, our attention turns to a question that has haunted humanity for as long as we've looked at the stars. Are we alone? It's perhaps the most profound question in all of science, and the most unsettling. In a universe filled with hundreds of billions of galaxies, each containing billions of stars and likely trillions of planets, it seems almost absurd to imagine that Earth is the only world to harbor life. And yet, despite decades of searching, despite our telescopes scanning the skies and our probes exploring nearby worlds, we have found nothing. No alien broadcasts, no interstellar beacons, no unmistakable signs of technology or civilization beyond our own. The silence of the cosmos is deafening, and this silence has a name: the Fermi paradox. The paradox is simple, yet devastatingly powerful. In the 1950s, physicist Enrico Fermi famously asked during a casual lunch conversation, "Where is everybody?" If intelligent life is common, he reasoned, then at least some civilizations should have developed interstellar travel long before us. Given enough time and the age of the galaxy, they could have colonized every star system, leaving visible evidence everywhere. But there's nothing. Our instruments detect no alien structures, no vast networks of signals, no stellar engineering projects like Dyson spheres. The universe appears empty of intelligent life, or at least of any life advanced enough to make itself known. This contradiction between the high probability of life and the total absence of evidence is what makes the Fermi paradox so haunting. Over the years, countless solutions have been proposed, each one offering a different lens through which to view the silence. Perhaps intelligent civilizations are rare, arising only under a narrow set of circumstances, a cosmic lottery so improbable that Earth may indeed be unique. Others suggest civilizations self-destruct before they can reach the stars, annihilating themselves through war, resource collapse, or uncontrolled technology, a sobering mirror for humanity's own trajectory. There's also the Great Filter hypothesis, which argues that somewhere between the emergence of life and the rise of galaxy-spanning civilizations lies an almost insurmountable barrier. It could be the leap from single-celled to multicellular life, or the challenge of surviving one's own technological adolescence. If the Great Filter lies behind us, humanity may be among the lucky few who made it through. But if it lies ahead, it could mean our doom is still to come. Other explanations are less grim but equally fascinating. Perhaps the universe is teeming with life, but most civilizations are uninterested in communication, preferring to look inward into virtual worlds or dimensions beyond our perception. Some may use communication methods we can't yet detect, neutrinos, gravitational waves, or quantum entanglement instead of radio signals. Others may have already visited, but at times or in forms we can't recognize. Transient probes, self-replicating nanomachines, or even life forms based on principles so alien we mistake them for nature itself. Still others point to the idea of the zoo hypothesis, which proposes that advanced civilizations are deliberately avoiding contact, allowing humanity to evolve naturally, much like we observe animals in a protected reserve. The silence, in this view, isn't indifference, it's intentional. And yet, even if the galaxy is quiet, we continue to search for technosignatures, traces of advanced technology scattered across the stars. SETI, the search for extraterrestrial intelligence, has spent decades listening for radio signals from other civilizations, scanning millions of frequencies with ever more sensitive instruments. But so far, all we've found are the whispers of nature, pulsars, quasars, and cosmic static. A few intriguing anomalies, such as the WOW signal in 1977 or repeating narrowband bursts, have sparked debate but never confirmation. Modern searchers now go beyond radio waves, looking for other potential technosignatures, artificial light from distant cities, waste heat from massive structures, or even chemical imbalances in exoplanet atmospheres that could indicate industrial activity. The cosmos is vast, however, and our current technology can barely scratch its surface. If alien civilizations are out there, their signals might be faint, fleeting, or encoded in ways beyond our current comprehension. Some scientists have even proposed that intelligent civilizations could hide themselves intentionally. If the universe harbors both peaceful and predatory species, then broadcasting one's presence might be dangerous, like shouting into a dark forest without knowing who's listening. A civilization advanced enough to manipulate its environment could cloak itself from detection, absorbing or redirecting light to remain invisible. This concept, known as cosmic camouflage, has even been simulated using hypothetical materials that could conceal a planet's heat signature or optical presence. It raises a chilling thought. Perhaps the stars around us are not lifeless, merely silent by choice. The galaxy could be full of civilizations quietly watching, each unwilling to reveal itself first. But life doesn't need to be intelligent to be profound, and in recent years, attention has turned to the icy moons of our solar system, especially Europa, Enceladus, and Ganymede, as likely havens for microbial life. Beneath Europa's frozen crust lies a vast subsurface ocean, kept liquid by tidal heating from Jupiter's immense gravity. Similar oceans exist on Enceladus, Saturn's tiny but active moon, whose geysers spew plumes of water vapor and organic compounds into space. These environments resemble the deep-sea hydrothermal vents on Earth, where life thrives in total darkness, drawing energy from chemical reactions rather than sunlight. If microbes can exist there, living off sulfur, methane, or hydrogen, it would mean that life is not a rare miracle of Earth, but a cosmic inevitability. Perhaps microbial life is the rule, not the exception, and intelligence is merely one possible branch on an immense evolutionary tree. The search for alien life, intelligent or otherwise, is more than a scientific endeavor. It's a reflection of our own place in the universe. The silence we hear when we listen to the stars could mean we're alone, the first to awaken in a cosmic dawn. Or it could mean the galaxy is alive with civilizations so advanced they have no need for our primitive signals. Either way, the question forces us to confront what life means and what our future might become. In the end, the search for others is also the search for ourselves, for meaning, connection, and our place in a universe that, whether silent or singing, still calls us to listen. Having explored the cosmic silence and the possibility of life beyond Earth, we now descend into a realm smaller, stranger, and infinitely more elusive, the quantum world, where the rules of reality itself dissolve into mystery. If the vastness of space humbles us, the quantum realm bewilders us, revealing that beneath the apparent stability of the universe lies a ceaseless storm of uncertainty and invisible motion. Every particle, every field, every flicker of energy exists in a haze of probability rather than certainty. Here, space isn't empty, time isn't absolute, and even nothingness is alive with activity. In this microscopic theater, the fundamental structure of reality and the fate of the cosmos may be written in equations we have only begun to glimpse. One of the most profound insights of modern physics is that even the vacuum of space is not truly empty. Quantum theory tells us that what we call a vacuum is, in fact, a restless sea of energy, a foam of fleeting particles that appear and vanish in unimaginably short timescales. These are quantum fluctuations, spontaneous bursts of existence where pairs of particles and antiparticles emerge from the void, borrow energy from the universe, and annihilate each other almost instantly. It's as if reality never sits still, constantly bubbling with potential. These fluctuations are not mere abstractions. They have measurable consequences. They influence how atoms behave, how stars shine, and even how the universe itself evolves. During the Big Bang, it's believed that quantum fluctuations were magnified by cosmic inflation, imprinting the tiny irregularities that would later grow into galaxies and clusters. In a profound sense, everything we see, every star, every planet, every human being, owes its existence to random quantum ripples in the vacuum. But what exactly is the fabric of that vacuum? Is space itself continuous, like a smooth sheet, or granular, made of discrete units too small to perceive? At the smallest conceivable scale, the Planck length, about 10 to the negative 35th meters, our current physics breaks down. Below this threshold, concepts like distance or location lose meaning. Many physicists suspect that space-time itself might be quantized, made up of indivisible atoms of space and time, forming a kind of cosmic lattice. This idea arises in theories such as loop quantum gravity, which envisions space-time as a network of tiny loops woven together like a quantum fabric. If true, it would mean that the smoothness we perceive in the universe is an illusion, that space, at its deepest level, is granular, vibrating, and constantly fluctuating. Detecting this structure directly is beyond current technology, but experiments looking for slight distortions in light or gravitational waves may one day reveal whether the universe is built from a quantum geometry. Then there's the enigma of quantum entanglement, one of the strangest phenomena ever discovered. When two particles become entangled, their properties become linked in such a way that a change in one instantly affects the other, no matter how far apart they are. Einstein famously called this spooky action at a distance, because it seems to violate the principle that nothing can travel faster than light. Yet, experiments have confirmed entanglement countless times, across distances of many kilometers, and possibly even across cosmic scales. The mystery lies in how this connection persists. Some theorists propose that entanglement may be a fundamental aspect of space-time itself, that the geometry of space is built from quantum entanglement. In this view, the links between particles are not just coincidences, but the literal threads that weave space together. If true, then space-time, gravity, geometry, even distance could all emerge from the quantum relationships between particles. Entanglement wouldn't just be a quirk of quantum physics, it would be the foundation of reality itself. But how do we reconcile this quantum world, where uncertainty reigns and probabilities rule, with gravity, the smooth, deterministic force described by Einstein's general relativity? For nearly a century, physicists have tried to merge these two great pillars of science into a single framework, a theory of quantum gravity. And so far, the universe refuses to yield its secret. Gravity describes the curvature of space-time caused by mass and energy, while quantum mechanics describes particles as probability waves interacting through uncertainty. At normal scales, the two coexist peacefully, but near singularities, black holes, and the Planck scale, they clash violently. The search for unity has given rise to bold ideas. String theory, which envisions every particle as a vibrating strand of energy existing in higher dimensions, and loop quantum gravity, which quantizes space-time itself. Both promise to explain how the universe behaves at its most fundamental level, yet neither has been conclusively proven. Somewhere between quantum theory's indeterminacy and relativity's smooth curvature lies a truth that could redefine everything we know, a unified theory of everything, the ultimate key to the cosmos. And perhaps the most staggering problem of all, one that highlights how incomplete our understanding remains, is the vacuum energy problem, sometimes called the cosmological constant problem. Quantum theory predicts that the vacuum of space should contain an enormous amount of energy, so much that, according to the equations, it should have caused the universe to expand so violently that no galaxies, stars, or atoms could ever form. But observations show the opposite. The actual vacuum energy, or dark energy, is incredibly small, about 120 orders of magnitude smaller than quantum field theory predicts. This is often cited as the worst theoretical mismatch in the history of science. Why is there such a vast discrepancy between the energy we calculate and the energy we observe? Some suggest that quantum contributions cancel each other out almost perfectly, a cosmic balancing act of positive and negative energies. Others speculate that the value of vacuum energy is simply one of many possible outcomes in a multiverse, and we just happen to live in a universe where it allows life to exist. Whatever the explanation, it's clear that our equations describe a universe we do not yet fully understand. At the intersection of quantum mechanics and cosmology, we glimpse a universe far stranger than imagination allows, a reality where empty space boils with invisible energy, where time and distance may be illusions, and where every particle is entangled in an infinite web of connection. The mysteries of the quantum realm remind us that beneath the stars, beneath even the atoms themselves, lies a level of existence that is both incomprehensible and essential, the ghostly foundation upon which the entire cosmos stands. From the mysteries of the quantum realm, where the very fabric of reality trembles with uncertainty, we turn our gaze to the ultimate question: what is the fate of everything? The universe has lived for nearly 13.8 billion years, expanding and evolving from a sea of hot plasma into a cosmic web of galaxies, stars, and life. But like all things born of time, it must one day face an ending. Whether it ends in fire, ice, collapse, or transformation depends on the invisible forces guiding its expansion: dark energy, gravity, and the deep laws of space-time itself. In contemplating the future and fate of the universe, we are also contemplating the destiny of everything that ever was, every star, every atom, every dream. There are three great possibilities for how the universe might end, each both awe-inspiring and terrifying. The first is the Big Rip, a fate driven by dark energy's relentless acceleration. If dark energy continues to grow stronger with time, rather than staying constant, it will eventually tear the universe apart. Galaxies will drift farther and farther from each other until even gravity itself cannot hold them together. Stars will be pulled from galaxies, planets from stars, and eventually atoms from themselves as space expands faster than light can travel. In the final moments, the very fabric of space-time will be shredded, and the universe will dissolve into pure, expanding emptiness. In this scenario, everything, matter, light, and even the laws of physics, disintegrates in a cosmic act of unmaking. A gentler, yet equally haunting outcome is the Big Freeze, also known as the heat death of the universe. In this future, dark energy remains constant, and the universe continues expanding forever. Over billions of years, galaxies will drift apart until each becomes isolated, surrounded by eternal darkness. Stars will burn out one by one, their ashes cooling into white dwarfs, neutron stars, and black holes. As time stretches on, even these remnants will fade. Black holes will slowly evaporate through Hawking radiation, releasing their energy back into the void. Eventually, the cosmos will reach thermal equilibrium, a uniform sea of faint radiation and subatomic particles, with no structure, no light, and no life. Time itself may lose meaning as nothing happens anymore. No events, no changes, just a silent expanse approaching absolute zero. It is the ultimate entropy, the final whisper of a once-living universe. The third possibility is the Big Crunch, the mirror image of the Big Bang. In this scenario, the expansion of the universe eventually slows and reverses, pulled inward by gravity's might. Galaxies would begin to move closer again, stars would collide, and the cosmic background radiation would heat up as everything compresses. Eventually, the entire universe would collapse into itself, all matter and energy converging into an unimaginably dense singularity, perhaps setting the stage for something new. The Big Crunch could, in theory, give rise to a new Big Bang, beginning the cycle anew. While current evidence suggests that the universe's expansion is accelerating rather than slowing, it's possible that dark energy could change over time, turning from repulsive to attractive, triggering a cosmic collapse billions or trillions of years in the future. If so, the universe may not die, but instead reincarnate, reborn from its own ashes in a grand cycle of destruction and creation. This idea leads to one of the most intriguing theories in modern cosmology: cosmic recycling. According to some models, the universe may not have a single beginning or end, but rather undergoes an eternal sequence of births and deaths, expanding, collapsing, and expanding again in endless repetition. Each cycle erases the memory of the one before, yet perhaps leaves subtle imprints in the fundamental constants of nature. This concept, sometimes called the cyclic universe or ekpyrotic model, offers a poetic symmetry that creation and annihilation are two halves of the same cosmic heartbeat. A related idea, eternal inflation, suggests that our universe is merely one bubble in an infinite cosmic foam, where new universes are constantly being born. In this model, inflation, the rapid expansion that followed the Big Bang, never truly ended. Instead, it continues eternally in other regions, spawning countless pocket universes, each with its own physical laws, constants, and perhaps even dimensions. Our universe may be one of trillions, a single shimmering droplet in an infinite sea of reality. And what of humanity in all this? Could we, or our descendants, ever witness the end, or the beginning, of another cosmos? In the near term, our species' survival depends on mastering technology, spreading beyond Earth, and perhaps even beyond the Milky Way. Yet in the far future, even the most advanced civilization would struggle against entropy's slow inevitability. Still, some scientists speculate that intelligent beings might find ways to migrate between universes, using wormholes or quantum tunneling to escape a dying cosmos into a new one. Others imagine civilizations harnessing the energy of black holes, or storing consciousness in quantum substrates, surviving in forms we can scarcely imagine. Perhaps, in the final seconds before the universe fades to black, some echo of intelligence will remain. A spark of awareness watching the last photons flicker out. And when the next universe ignites, that spark might be carried forward, a cosmic memory, an echo of life continuing across the ages. In contemplating the universe's fate, we are reminded that endings and beginnings are not opposites. They are phases of the same eternal process. Whether the cosmos freezes, collapses, or renews, it will continue to evolve according to the laws that brought it forth in the first place. The universe has already transformed from pure energy to matter, from chaos to structure, from darkness to consciousness. Whatever comes next, we are part of that grand story, fleeting observers of an infinite tapestry woven from light, time, and the boundless curiosity that drives us to ask what lies beyond the stars. And now, at the end of our journey through the mysteries of the cosmos, from the birth of time to the possible death of everything, we come full circle. After exploring black holes and galaxies, quantum foam and alien life, one truth becomes clear. The more we learn about the universe, the more we realize how little we truly understand. Every question answered opens 10 more. Every discovery deepens the mystery. The cosmos is not a solved puzzle, but an ever-expanding labyrinth, one that humbles us even as it inspires us. We've mapped the stars, landed on the moon, peered into the earliest moments after the Big Bang, and yet the most profound aspects of reality, dark matter, dark energy, the origin of existence, the nature of consciousness, remain hidden behind a veil we've only just begun to lift. And that's the beauty of it. The universe doesn't hand us its secrets easily. It invites us to wonder. Every unsolved riddle is not a failure of understanding, but a spark, a challenge that drives science forward. When ancient stargazers traced patterns across the heavens, they set in motion a legacy of curiosity that continues today in the laboratories, observatories, and minds of scientists around the world. From Galileo's telescope to the James Webb Space Telescope, from equations written on chalkboards to probes sailing beyond Pluto, humanity's greatest strength has always been its refusal to stop asking, why? It is this relentless curiosity, the hunger to know, to see, to understand, that transforms our ignorance into discovery, our confusion into awe. We must remember that the unknown is not our enemy. It is not a void to be feared, but an ocean to be explored. Every mystery, whether it lies in the heart of a black hole, the whisper of a quantum fluctuation, or the flicker of a distant star, is an invitation to grow. The universe is not withholding its truth from us. It is showing us, in its silence and vastness, that knowledge is a journey without end. There is no final answer, only deeper questions. And in that endless pursuit lies the essence of what it means to be human. Someday, our species may fade. The stars that warm us will burn out, and the galaxies will drift apart into the cold eternity of the cosmic night. But as long as even one mind looks upward with curiosity, as long as one heart feels wonder beneath the stars, the universe will never be truly silent. We are the way the cosmos has come to know itself. Our questions, our dreams, our search for meaning, they are not separate from the universe's story. They are the universe's story. So as we close this exploration of 100 space mysteries science can't yet explain, let it not leave us with despair, but with inspiration. Because every unanswered question reminds us that existence is still unfolding, that there are wonders waiting just beyond our reach. And perhaps that's the greatest mystery of all, that in a universe so vast and ancient, we are here, thinking, feeling, and daring to ask what lies beyond. The unknown isn't a barrier, it's a beginning. The greatest adventure in existence, written across the stars, waiting for us to keep searching. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.